into this iron carbon diagram?
No, sir.
Hmm? It's clear to all. Okay, जिस तरह हम स्टील में there are carbon steels, so carbon steels they mainly contain so that specified amount of carbon. उसमें और कौन से एलिमेंट्स हो सकते हैं कार्बन स्टील्स में नॉर्मली? Small amount of say manganese, very small amount of silicon, and then phosphorus sulfur in the control state. So what about cast irons? Cast irons में क्या होता है? What are the main constituents of cast irons? Hmm? Zuhair? Anybody else? People from materials? Do you hear me? Audible?
सर ग्रेफाइट के
Yes, sir.
कुछ इस तरह के फ्लेक्स हो सकते हैं शायद.
Okay, graphite is carbon. So you normally see with in cast irons, cast iron is basically a ternary alloy. So there is iron, carbon, and silicon, right? So carbon is essential, so is silicon. So you see most of the cast irons, they other than iron and carbon, they do contain some amount of silicon as well. Okay, so moving to the next slide. So look at this one. So this undergoes this eutectide transformation from gamma to say this perlite, which is a mixture of alpha and iron carbide. So alpha at this point, just below this eutectide reaction of 727 degrees centigrade, this contains 0.02 weight% carbon and iron carbide, which is 6.67 weight%. This kind of structure, but at lower temperature, lesser carbon is soluble in alpha iron, so its carbon content decreases, right? So this is all eutectic, so all eutectoid mixture perlite. This would be alpha plus perlite. So we'll come back to the other one. Okay, this is the the layered structure that form is similar that forms in the eutectic. So the difference is basically that in eutectic there is a liquid involved, while in eutectile there is a solid, but again there is a short interference ahead of this interface that forms this kind of alternating layered structures or other structures. So in case of perlite, this is a layered structure like this. Okay, look at this one at point C. This is point C. It's homogeneous gamma solid solution. At point D, alpha is formed. Now this is a two-phase field, alpha plus gamma. Gamma is this FCC solid solution, and alpha that forms below this line, this transformation line. So at point D, we have alpha plus gamma. This alpha phase is called pro-eutectide alpha. ठीक है, जो कि आपका eutectoid transformation से पहले बना है. Then at this point, this eutectoid transformation happens. So this remaining gamma transforms into this perlitic mixture or eutectide mixture. ठीक है, ये जो आपको लेबुलर नजर आ रही है, this is pro-eutectide alpha, यानी ये eutectoid transformation से पहले बना है. ठीक है, then there is a eutectide transformation. Okay, this is what it looks like. अगर आप mild steel means having this low value of carbon somewhere, I mean say 0.1 to 0.3 weight percent carbon in iron. So if you look at the structure, so you will see this kind of image under a microscope. White region is pro-eutectide alpha, while this dark region you can see layers, lines. So this is perlite or eutectoid mixture. Okay, so this is the morphology of some steel which is a hypoeutectoid steel. Okay, hypoeutectoid means composition lies in the same starting from here to this point. These are all hypoeutectoid steels, and those which have carbon content which is higher than this eutectoid composition, they are called hypereutectoid. This is hypo, this is hyper, right? So this is a hypoeutectoid steel. You can see alpha, proeutectoid alpha, and perlite. So fraction, you can use the Neber's rule and find out the fraction. ये कितनी fraction है इसकी? Fraction of perlite and fraction of proeutectoid alpha. वो भी आप find out कर सकते हैं. ठीक है? Now, if we go to hypereutectoid range, so the composition is having greater amount of carbon compared to this eutectoid or hypereutectoid compositions. So pulling from this range, let's say we start from here. So this will produce. अच्छा जब ये line cross होगी, what do you think? What will form? It's all gamma. When this line is crossed, iron carbide, not alpha, iron carbide particles will form. ठीक है, जो phases में बनेगा वो कौन सा बनेगा? Iron carbide, और इसकी content increase होगी. ठीक है, till we reach this eutectoid point. Right? At this point, there is again a eutectoid reaction, and the eutectoid mixture perlite forms, which is of some type. This ये इस तरह की उसकी shape बनेगी. So there will be pro-eutectoid, ये जो आपको लंबा सा नजर आ रहा है, pro-eutectoid आयरन कार्बाइड, यहाँ क्या था? pro-eutectoid alpha, यहाँ pro-eutectoid iron carbide and eutectoid mixture of iron carbide and alpha. ओके, ये क्लियर हो रहा है? am I audible? आवाज प्रॉपरली आ रही है आपको?
यस सर।
Okay.
यस सर, आ रही है।
अच्छा, नो अगर आप देखें तो इट्स जस्ट लाइक फिल्म. I'll show you the structure here. Okay, so this is, ये क्या? प्रो यूटेक्टाइड सीमेंटाइट और Fe3C because of slow cooling. Equilibrium diagram, all these structures, these morphologies form because of the very, very slow cooling. So you can see a layer of iron carbide forming at the boundaries. Well, in between there is perlite, which is the eutectoid mixture. Eutectoid, ठीक है, iron carbide plus alpha. And this is pro-eutectoid iron carbide. यहाँ पे क्या बन रहा था? Pro-eutectoid alpha. ठीक है, यहाँ क्या बन रहा है? Pro-eutectoid iron carbide. Now iron carbide is a soft material, a hard material, or a brittle material? क्या कहेंगे?
सर ब्रिटल होगा।
Brittle होगा? Sure?
यस सर, मेरे ख्याल में।
Any other person? Any other idea? Iron carbide, is it brittle material? Is it soft material? क्या है? Hmm? Laba, what do you think?
सर हार्ड मटेरियल होगा, आई थिंक।
I think two of the students are missing in this class. Laiba and the other person comes from again. Are they there? Okay. Okay, as iron carbide is a very hard material, very brittle material. So that means if there is a continuous film that forms in the structure, that will make the material very brittle. So brittle materials, they undergo very fast cracking, fast fracture. So this kind of material as a whole will act as a brittle material. ठीक है? Is it clear?
Yes, sir. Yes, sir.
Okay, so next facts elements in iron that it makes on the transformation temperature, especially the eutectide temperature and the eutectide temperature and the eutectide composition. So first we look at the eutectide temperature for for carbon steels where carbon content is not less than one. So you can see the following elements that say if we look at titanium, a small amount of titanium they say at say about 1%, detected temperature is above titanium. Similarly, all these elements, molybdenum, silicon, these increase. Chromium also increases, but has a lesser effect. While manganese and nickel, they decrease the eutectoid temperature. So, looking at the diagram, what does it tell you about these elements? They push the eutectile temperature to higher temperatures. That means they mostly stabilize alpha phase. Though press is the gamma phase. It means they expand the field of gamma to lower temperatures, push the gamma field upward. Okay. Show you again in the diagram. That means it is decreasing the extent of this field, gamma. If something decreases down, decreases it, add that element, it will stabilize gamma at a lower temperature. So for other ones that pushes up, that means they more or less act as stabilizers of alpha, pushing the alpha field to higher temperature. ओके, ये चीज आपको कुछ क्लियर हुई है ये पॉइंट here? Is it a bit clear?
Yes, sir.
Am I audible? ठीक है,
Yes, sir. ये
इनका क्या
इफेक्ट
test
ऑफ
है?
फिलिंग एलिमेंट की
Alpha
समझ आ गई।
stabilizer. समझ आ गई? Okay, very good. So this
Yes,
is
sir.
detected composition, this is the lying element, right? So this अगर आप देखें तो ये क्या कर रहे हैं? Detected concentration को in terms of weight percent carbon, ठीक है? Small amounts So that means कि eutectoid so eutectoid reaction is so eutectoid reaction can happen at point carbon content कितना है? What is the carbon content in eutectoid steels or eutectoid composition in iron carbon diagram? कितना है इस eutectoid content जो है?
0.8%.
हम 8% कार्बन तो यहाँ पे जो है वो कितने परसेंट टाइटेनियम
Recording
सर आपकी
stopped.
आवाज नहीं आ रही। अब्दुल्ला आपने क्या किया? सर को निकाल दिया, क्या किया आपने?
मैं किस तरह सर को निकाल सकता हूँ? सर का कनेक्शन नहीं सही।
यार किसी को पता है रास्ते खुल गए?
Recording in progress.
ओके प्लीज रिप्लाई डू यू हियर मी
सर आपकी आवाज थोड़ी सी इंटरप्शन है, हम आपको सही से सुन नहीं पा रहे हैं सर।
Recording stopped.
यार किसी को पता है रास्ते खुले हैं या नहीं?
कल रात तक तो बंद
फिलहाल
थे,
तो
आज
बंद,
का नहीं पता।
फिलहाल तो बंद है।
ये दरबार कैंट जो नहीं पहुंच सकते, ये पहले बंद कर देते थे ना हसनबदाल से, वो बंद है या वो खुला हुआ है? किसी को पता है?
यहाँ से गाड़ियां जो जा रही हैं ना वो नहीं जा रही, लोकल गाड़ियां। बाकी रास्तों का डिटेल नहीं पता।
अच्छा, ये तो बहुत बैड सीन है यार।
मोटरवे सिर्फ इस हद तक खुली है कि इस्लामाबाद से पेशावर तक आ सकते हैं, लेकिन इस साइड से आप इस्लामाबाद नहीं जा सकते। बस इसी ये बंद है, वो बाकी वहां से आ सकते हैं।
मतलब इधर से जिधर मर्जी जाओ, पेशावर के पीके में जिधर मर्जी जाओ।
हाँ, इधर
अब
से जा
मैं तो
सकते हैं, लेकिन उस
यार,
साइड से
मैंने
आप
वाह
नहीं।
कैंट जाना है, मैं जा सकता हूँ किसी तरह? चलो देखते हैं क्या बनता है यार।
लोकल तो मुश्किल है, अड्डे पे जाके चेक करना पड़ेगा आज। कल तक तो गाड़ियां नहीं चल रही थी।
दुल्ला भाई, आप किधर हो? इधर यूनिवर्सिटी में हो या उधर आप घर हो?
नहीं नहीं, मैं यूनिवर्सिटी में ही हूँ। मैंने कल जाना था पर अड्डे पे गया हूँ तो गाड़ियां ही नहीं थी, मैं पिंडी जाना था।
तो आप क्लास के बाद आ जाना, हम दोनों इकट्ठे सर्च करते हैं।
आप किधर हैं अभी?
मैं ये है ना, ये जो हेमलेट मोड़ है उसके पास हूँ।
ठीक, चले मैं बाद में रब्ता करता हूँ आपसे क्लास के बाद।
क्लास के बाद रब्ता करें ना, अगर कोई स्पेशल करानी पड़ी तो वो भी बंदा करा के फिर चला जाता है, शेयरिंग करके।
सही, सही हो गया।
तुमने सिर्फ फोन जो है वो अटेंड करके रखा हुआ है? यार अभी सर से कोई बोलेगा कि क्लास बस कर दें, वो जो है रुक रहा है बार बार ना।
Recording in progress.
हेलो।
यस सर।
ओके, कुछ बेहतर सॉरी, देर इज एन इंटरप्शन, सम बेटर ओरिएंटेशन। तो अब कुछ आ सबको?
सर आपकी आवाज़ स्टिल वो इंटरप्शन है, कट कट सी आ रही है, सही से आवाज़ नहीं आ रही सर, ग्लिचेस हैं।
Okay,
सर
so
मुझे भी नहीं आ रही, मुझे
let's
तो
start.
भी नहीं लगता है।
I think it get better in a minute or two. कुछ बेहतर हुई है?
आवाज आ रही है सर, स्क्रीन नहीं आ रही मेरे पास।
हम्म। Okay, is it better now? Is it
यस सर,
better?
यस सर।
यस
यस
सर।
सर।
Okay, so we move on to how we determine these phase diagrams, right? So first way to determine this is to record cooling curves. So how can you record cooling curves? Cooling curves आप कैसे record कर सकते हैं? Pure elements and congruent melting phases, compounds, they melt at a single temperature. But alloys or say some range of melt over a range. So we can determine cooling curves, and by using the cooling curves, we can at least isomorphous diagrams, they can be easily drawn. So we'll see an example of these cooling curves. Okay. Differential scanning calorimetry. Scanning calorimetry. Are you all familiar with DSC?
No, sir.
Have you worked with DSC or used DSC? Hello?
No, sir.
Yes, sir. Familiar.
Is थोड़ा ऊंचा बोले आप, बहुत स्लो बोल रहे हैं, मुझे आपकी आवाज सुनाई नहीं देती, ताकि मुझे पता चले
No, sir. We are not familiar with this
कि
DS.
क्या कितनी डिटेल तक हमने डिस्कस. Okay. Okay, let's quickly go through the list and then I'll discuss. Other thing is thermomechanical analysis. Then DTA, it's normally also attached with the DSC. Dilatometry, measuring dimensions with phase transformations, either they involve expansion, contraction, or change in or distortion, some change in dimensions. Metallography is also a tool that is used to prepare what compositions and what kind of treatment theme. Again, you can use the SCM and EDS. So EDS is emissions of the phases. Diffraction gives you idea of the crystal structure. So obviously that will, with the help of XRD, X-ray diffractometer, you can find out the crystal structure of the new composition of the new phase. Transmission electron microscopy is also a powerful technique for high resolution images and looking deep into the alloys and their structures. So these all different techniques are used to determine phase diagrams. Cooling curves. Okay, if you look at pure copper, that is being cooled from 1400, this is time, on y-axis is temperature. So it starts to cool, let's say from 1400 degrees centigrade. With the passage of time, it reaches some temperature, that is its equilibrium melting temperature. At that melting point, melting temperature, the time will increase and the temperature will not decrease with increase in time or with the passage of time until all of the liquid copper is solidified. So there is no change in temperature. We talked about equilibrium slow cooling, no change in temperature. All of the liquid is converted into solid. So that takes this much time. Then again, it starts to cool, okay, to lower temperatures. This is for pure copper. Similarly for pure nickel, but for alloys with different composition. Let's say This is a copper nickel alloy, which is an isomorphous system, soluble in liquid and solid conditions. So let's say if there's 20% nickel at this point, which is the liquidus, there is a change in slope of this line, and again at solidus there is again change in slope. So faster as the temperature is decreasing at a faster rate than at within this liquid plus solidus region, there is a change in slope, the cooling becomes slower. So as we move towards higher temperature, towards the nickel, this range for the alloys for cooling when the two phases exist. Okay, am I audible?
Yes, sir.
To hear
Yes,
me?
sir.
Okay. So for pure nickel, now these points, so pure metals A, B, and C, D, and for these alloys, the range is okay for pure alloys. These points, and pure metals, these points, and for alloys, these ranges. If we mark the start and end point, and then join the start and end points, we'll get a loop like this. Okay, liquidus and solidus. Okay, so in between there is liquid plus alpha. Above this temperature, liquidus, there is liquid. Below the solidus temperature, all solid. So for let's say for simpler type of soluble systems, this approach can be adopted, and for some other systems as well. Okay, अगर आप ये देखें, this I think is a dilatometer, which measures the dimension, change in dimensions when when a material is heated or when it's cooled. So when there is a phase transformation, there is a change in dimensions, let's say in length. That change is measured, and that denotes the start of transformation. If there is a change, then there is a transformation, phase transformation that is happening. So some phases they have a larger volume, and some have smaller volume for the same amount of material. So that's how this thing this is another equipment that helps you in measurement, in these drawing of these phase diagrams. Okay, so this is a DSC curve, DSC graph. On this y-axis, there is heat flow, and on x-axis is temperature, right? So when if you take a small amount of material, you heat it. So when there is a transformation, that means either if that is an exothermic reaction, heat will be evolved, and if that is an endothermic reaction, heat is absorbed. Right? So for that temperature, either there will be an increase in heat flow or a decrease in heat flow. Let's say if this is endothermic, increase in heat flow, this shows as this peak. And if there is an endothermic reaction, and the heat flows in this direction, so that will appear as a trench or a dip. Okay. So let me before going into detail of this DSC, let me schedule the other meeting, because this is the time of this meeting is almost up. So we have to do one more. I quickly schedule it, and we start from here, DSC. Okay. Am I audible? Hearing me?
Yes, sir.
Yes, sir.
Yes, sir.